Welcome to the next module of our soot-free and zero-emission urban bus fleets technology transition curriculum. Today in Module 3, we will be discussing the infrastructural considerations for different soot-free and zero-emission technological pathways. Before we begin, here are some key terms that we will come across. Electric Vehicle Supply Equipment, or EVSE, is a general term that refers to the machine that supplies electric energy to charge battery electric buses. It is used interchangeably with other terms like charging station and charging point. Supervisory Control and Data Acquisition (SCADA) is an industrial term that describes a control system architecture comprising computers, networked data communications, and graphic user interfaces for high-level process supervisory management. In an electric power system, switchgear is composed of electrical disconnect switches, fuses, or circuit breakers used to control, protect, and isolate electrical equipment. Switchgear is used to de-energize equipment to allow work to be done and to clear faults downstream. HT means high tension or high voltage, where small current is used with very high voltage. LT means low tension, where low voltage is used with a very high current. A distribution transformer is the type of transformer that performs the last voltage transformation in a distribution grid. It converts the voltage from the one used in the transmission lines to one suitable for household and commercial use. Cryogenic storage is a specialized type of vacuum flask used for storing cryogens, which are extremely cold, small amounts of liquid that expand into very large volumes of gas. In this module, cryogens refer to hydrogen. The next keywords are about battery electric bus charging. Depot charging and en route charging refer to different charging locations and arrangements, whether the EVSE is installed in a depot or outside of a depot on a service route. A conductive charger has its electricity transferred by conduction or direct contact between the charger and the bus battery. Inductive charging relies on induction to supply electricity to vehicles without direct contact between the power source and the bus. While both overhead chargers and plug-in chargers are conductive charging devices, the overhead charger uses a pantograph located on top of the bus, while plug-in chargers use a plug and work more like charging an appliance or electric passenger vehicle. Here are the learning objectives for today's module. Appreciate the importance of infrastructural readiness for bus fleet technology transitions. For diesel buses, understand why higher quality diesel or 10 ppm sulfur diesel for soot-free Euro 6 or EPA 2010 buses is needed, and how cities can overcome national circumstances. For battery electric buses, learn the common battery charging options, including conductive charging, AC or DC charging, the different speeds and standards, and the pros and cons of different charging solutions from the perspectives of cost, space needs, and operability, and how to quantify power demand during peak hours and the importance of working with utility companies. For hydrogen fuel cell electric buses, understand the physical infrastructural components for hydrogen production and methods suitable for bus operators. First, let us talk about the infrastructure for soot-free diesel buses. Soot-free diesel buses' greatest infrastructural challenge is the availability of ultra-low sulfur diesel, which is diesel with sulfur content lower than 10 parts per million. When diesel fuels containing sulfur content greater than 10 parts per million are used, efficiency of emission control technologies will be compromised. The risks involve immediate losses of pollutant conversion efficiency by sulfur poisoning, increased fuel consumption, and in the long term, risks to system durability. Therefore, it is not advisable to run Euro 6 diesel engines equipped with diesel particulate filters and selective catalyst reduction systems on Euro 6 or 50 ppm sulfur, for instance. In parts of Asia, Africa, and Latin America, domestic fuel production does not yet produce ultra-low sulfur diesel, and 10 ppm sulfur diesel has not yet made available nationwide in many countries of these regions. Countries like India and China have successfully adopted emission standards that mandate soot-free Euro 6 diesel on heavy-duty vehicles in the past decade. Elsewhere, Indonesia is investing billions of dollars in refinery upgrades to improve fuel quality, but will still need a few years before the diesel is 50 ppm sulfur. Big cities in some countries have higher quality fuels than the rest of their country, leading the way to better air quality. One example is Lima, Peru, which has 10 ppm sulfur diesel, even though the rest of the country still uses diesel with much higher sulfur content. For the most part, the production, import, and distribution of cleaner fuels are national policies and outside the control of city officials or operators. However, operators in these countries can explore special fuel supply options to overcome local refinery limitations that may be hindering ultra-low sulfur diesel production. For many bus operators, the biggest challenge of the technology transition is infrastructure for both battery electric and hydrogen fuel cell electric buses. Recall our earlier module on different vehicle technologies. Infrastructure is part of the capital investment expenditure that cannot be ignored. This figure shows the breakdown of total cost of ownership of a few different bus technology types in Sao Paulo. What's worth mentioning here is that the net infrastructure acquisition is highlighted in red and is an additional upfront capital cost that many operators find to be a major barrier. The importance of infrastructure is highlighted in virtually all cities that have attempted to electrify their fleets. Shenzhen is widely recognized as the electric vehicle capital of the world, and all of the city's public transit buses are zero emission. But even Shenzhen ran into problems when the city government's infrastructure plan between 2009 and 2012 did not anticipate such a rapid adoption of zero-emission buses in the final acceleration stage. It caused a shortage of charging infrastructure in the city that led to operational impediments and higher than necessary costs. For battery electric buses, operators need to think about where, when, and how to charge their buses to deliver high-quality, consistent service while keeping operations economical. For hydrogen fuel cell buses, the production, storage, and transportation of inflammable hydrogen fuel is also a critical factor. In short, careful planning before investing in infrastructure is critical and requires analysis of existing operations, energy consumption, and forecasting electricity demand for a full fleet of battery electric or hydrogen fuel cell buses. The concepts and practice of fleet-wide planning will be discussed in a future module. In the rest of this module, we'll go over the infrastructural components for battery electric and hydrogen fuel cell buses. There are, in general, two types of charging strategies for BEBs: depot charging and en-route charging. For depot charging, the charging equipment is installed at the depot, terminal, or maintenance facility. What's unique for battery electric buses is having the possibility of en-route charging, something which is not possible for other vehicles that do not follow predefined routes, such as taxis, freight trucks, and personal vehicles. Theoretically, it allows for indefinite bus operation. Some operators use a mixture of both depot and en-route charging. An example of this arrangement is in Vienna, Austria, where the existing electricity infrastructure for tram system is utilized for 2 electric bus routes, and the batteries are also charged at bus terminals. The next slide breaks down different options for both depot and en-route charging. The two options each have their own pros and cons. Depot charging has a lower initial capital investment, and because all the chargers are in the same space that operators already own, there are less permits and land rights issues. Operators can maintain the equipment more easily and don't have to worry as much about vandalism or other kinds of damage. Battery electric buses operating on routes can utilize the same facility at the same time. For en-route charging, one charger serves multiple buses, and the placement of charger along the route means buses don't have to carry huge batteries in order to have extended range. Lack of extended range via en-route charging not only increases cost, but also the weight of the bus. The limitation with this option is that each charging station can only service one bus route at a time. Another way to look at the charging infrastructure is through the physical interface of charging, which is how the BEBs are recharged. In most cases, charging is done via electrical conduction, and the physical interface is either a plug or a pantograph. Plug-in charging is exactly what the name suggests. Much like charging electric passenger vehicles, these plug-in chargers are ground-mounted in depots or maintenance facilities for overnight charging. Plug-in chargers are a matured charging option that has seen applications in bus operators around the world. One potential challenge for plug-in chargers is finding adequate space for many chargers. For a full fleet of BEBs, it may be more difficult and could require purchasing land or expanding facilities. Overhead charging is another method of conductive charging. Overhead charging equipment typically uses a pantograph where the moving parts are on the bus, or an inverted pantograph where the moving parts are on the mast. There are several providers of pantograph charging technologies today, and such systems are offered as an option by European and North American e-bus producers Proterra, Solaris, VDL, Volvo, and Van Hool. The advantage of overhead pantograph charging is that one charger can serve multiple buses, and when deployed in en-route charging scenarios, they can reduce the footprint of EVSE in depots and facilities, while allowing buses to carry smaller batteries for reduced weight and cost. Pantograph charging involves less labor to operate the charging station compared to plug-in chargers, and is therefore cheaper to operate. Depots in Europe have capitalized off of these advantages and usually use pantograph charging over plug-in chargers. However, if overhead pantograph system is deployed for en-route charging, the area footprints of EVSE could become an issue since operators don't normally own the road space. There are two other less common charging solutions. Inductive charging produces electricity across a magnetic field and is wireless. The absence of wires and connectors means inductive charging is ideal for short stops at bus stops and during layovers for en-route charging. However, wireless charging is not a conventional technology and is prone to electromagnetic interference-related challenges. There is no interoperability among different wireless charger service providers who use different standards. Finally, there's battery swapping technology, where depleted vehicle batteries are swapped with fully charged batteries. The time required for swapping may range between 2.5 minutes to 10 minutes, much quicker than the time taken to charge a battery to full. But additional time is still needed to recharge the batteries when they're offloaded from the vehicles during the charge. Battery swapping systems require battery swapping arms and battery movement systems. Battery swapping requires costly infrastructure for the swapping stations and a large number of batteries, and it offers limited flexibility as battery swap systems are often tied to certain vehicle brands. Like inductive charging, these are costly and less common for mass deployment purposes. The next distinction to make about EVSE is between AC and DC charging. To be clear, batteries onboard electric buses are charged by direct currents no matter the external electricity source. The distinction here between AC versus DC EVSE is whether AC to DC conversions happen in the bus or in the charger. For AC charging onboard the vehicle, electronics convert the AC power to the DC power that is required to charge the battery. As we will see in the next few slides, AC charging is not very powerful, limited by weight and space constraints by an onboard charger required to support high power levels at these relatively low voltages. For DC charging, the electronics required to convert power from AC to DC are placed outside the vehicle, and the DC charger provides DC power to the BEV. These chargers are currently capable of supplying power up to approximately 350 kilowatts, and future product forecasts indicate that power supply could be as high as 3 megawatts. Different physical interfaces mean different charging speeds. For AC charging, the capacity of the onboard charger and the AC power supply limit the capacity of AC charging. Lower power AC chargers, 20 kilowatts for example, are normally used for overnight depot charging to up to a battery in 10 hours, while faster chargers and connectors operating on three-phase industrial power supply like SAE J3068 enable quicker charging times thanks to the higher power output. DC chargers have the highest power and are sometimes referred to as fast chargers because a shorter amount of time is needed to fully charge the batteries. 50 kilowatt DC plug-in chargers are commonly used for charging e-buses, and 150 kilowatt DC plug-in chargers capable of charging 3 e-buses, one after another, are also available in the market. This high power delivery means that they are ideal to charge batteries for a short amount of time during en-route charging. Fast DC charging enables quicker turnaround times and thus requires fewer chargers, whereas slower charging means buses won't replenish their batteries in 8 to 12 hours. Additionally, to service a fleet of buses, more chargers are necessary. With higher power, the charging cables now need to be liquid-cooled for safety and reliability reasons. Pantograph charging with onboard bottom-up and off-board top-down configurations still also utilize direct current. DC pantograph charging technology is expensive and requires additional auxiliary infrastructure. Typical area requirements for a DC pantograph system and a DC plug-in system are considered to be similar. An industrial consortium named Charging Interface Initiative's High Power Commercial Vehicle Charging Task Force is developing high power charging tailored for commercial vehicles that can achieve a charging capacity of 1 to 3 megawatts. This technology is still in progress, but would make charging larger batteries onboard commercial vehicles like electric buses a much faster process. Rates of charging may affect battery durability for certain types of battery chemistries, so when planning for infrastructure, compatibility with buses need to be considered. Another way to distinguish charging is through the different charging standards and protocols of communication between BEBs and EVSE. In the United States, most BEBs are equipped with at least one of the three standard plug-in charging interfaces. For lower power AC charging, less than 20 kilowatts, the Society of Automotive Engineer SAE J1772AC interface is typically specified. For higher power levels, between 20 and 50 kilowatts, vehicles may be equipped with either a combined charging system Type 1 CCS1 or a CHAdeMO DC charging interface. Above 50 kilowatts, most vehicles will be equipped with the CCS1 DC charging interface. Chinese manufacturers' products follow the GBT20234 standard, and European BEBs have their own versions of the CCS standard. The number of charging standards in the market is sometimes confusing, especially for operators dealing with products from different countries. But there is space for negotiation and flexibility. In Santiago, Chile, BYD manufactured buses compatible with CCS2 standards, which are common in Europe, to make sure all its depots are future-proof and that different products from different manufacturers will have interoperability. Open ChargePoint is a communication protocol that allows open source communication between chargers and charging management system, and avoids proprietary charging management systems involvement. In other news, SAE adopted a new charging interface standard known as J3068 that is intended to replace the CCS1 interface in North America. J3068 is further compatible with the CCS standard used in Europe and harmonizes standards between the two regions. It is important to keep in mind the scale of investment in EVSE for battery electric bus fleets and what that means for space and power. One plug-in DC charger takes up around 0.8 meter squares of space. For a fleet of 100 buses charging simultaneously in a bus depot, that is a total footprint of at least 80 meters square, without considering spares. At the same time, if the buses are charging at 100 kilowatt each without a smart charging arrangements, the power demand would be at least 10 megawatts, which will likely require power distribution upgrades for existing facilities. This is on top of electricity consumption at the bus depot or maintenance facilities. If the combined electricity demand happens during peak demand hours, the energy costs will increase. This level of power puts operators in a different customer class and requires specialized service and connection to the substation. This hypothetical example illustrates how important utility companies and city governments are for BEB infrastructure. Operators agree. A World Resources Institute survey of Chinese bus operators found that land ownership and rights for facilities, grid capacity in old cities' electric power system, and integration of charging plugs into the power grid are among some of the biggest hurdles for BEB infrastructure. Successful deployments of BEBs around the world have demonstrated that utility providers must be engaged throughout the deployment process to discuss service and infrastructure needs, build grid capacity, and to negotiate electricity rate structures or preferential rates. Operators can optimize the charging strategy and timing to avoid charging buses during peak demand hours to save on electric bills. California's utility provider PG&E has introduced a special electricity plan for bus operators to charge their buses in anticipation of the state's target to convert all transit buses to zero emission by 2040. Bus depots and terminals are sometimes leased by the bus operators, and the land is usually a scarce resource in urban areas. So it requires consultation and dialogue with city officials and planning agencies to balance competing land uses and securing necessary permits. Let us now move on to another zero-emission bus technology, fuel cell electric buses, which are fueled by hydrogen. There are two main sources of hydrogen production. In the United States, most hydrogen fuel is produced through steam methane reformation, which is combining high-temperature steam with natural gas to extract hydrogen. Another method of hydrogen production is electrolysis of water, a process that is more energy intensive but takes advantage of inexpensive excess renewable energy, such as wind or solar, while avoiding the harmful emissions associated with other kinds of energy production. The term green hydrogen refers to hydrogen produced from water electrolysis using renewable power, and conversely, steam methane reforming is referred to as blue hydrogen. If the power required for electrolysis is 100% renewable, this can theoretically eliminate all greenhouse gas emissions. Production of hydrogen can either take place on-site where refueling takes place, or from a centralized supplier, which then delivers the hydrogen fuel. Hydrogen can be produced in either gaseous or liquid form. After the hydrogen is produced from the supply source, the other key component in FCEB hydrogen fueling infrastructure are storage tanks, which may either be low or high pressure and can exist in the form of a compressor, vaporizer for liquid storage, a refrigeration unit, or a dispenser that delivers the fuel to the vehicle. As mentioned in the previous slide, hydrogen production can either take place on-site or off-site, and hydrogen can either be produced in a gaseous or liquid form. Because hydrogen has a relatively low volumetric energy density, its transportation, storage, and final delivery to the point of use comprise a significant cost, and the production and delivery of hydrogen merit some careful planning. Each type of hydrogen fuel supply has its own advantages and disadvantages. Some considerations are: gaseous hydrogen are more economical than liquid, particularly because liquefaction requires a substantial amount of electrical energy. On the other hand, liquid hydrogen is much denser than its gaseous counterpart, so fueling stations relying on liquid hydrogen can store more fuel and reduce delivery frequency. Also, cryogenic storage at stations may use cheaper equipment by avoiding tube trailers and compressors, especially on a per kilogram hydrogen basis. For heavy-duty applications like buses, liquid delivery makes more sense economically because a centralized hydrogen liquefaction saves energy for the compression stage and purifies the fuel as impurities sink to the bottom. Gaseous hydrogen production and delivery solutions are increasingly looking like a niche market for low-volume, low-frequency uses. Producing hydrogen on-site requires available energy sources, either from electricity for electrolysis or natural gas for steam reformation. Transit agencies that want to minimize or eliminate the carbon footprint of on-site hydrogen production are considering utilizing renewable energy to operate hydrogen production equipment or reforming biogas. On-site facilities that produce hydrogen have relatively low delivery costs, but the cost to produce the hydrogen is likely to be higher because production volumes are less. Having hydrogen fuel produced off-site and delivered to a bus depot means less equipment to maintain, lower energy costs, and is a similar procedure to diesel delivery, which operators may be familiar with. A large centrally located hydrogen production facility off-site can produce hydrogen at a lower cost because it is producing more, but it costs more to deliver the hydrogen because the point of use is farther away as the hydrogen boils away. Ultimately, the storage option decision will still have to be informed by hydrogen consumption modeling, consultation with bus manufacturers, and space and location constraints. An ICCT study in 2007 reviewed hydrogen station deployments around the US and the world and found that many initial hydrogen stations were deployed at about $2 to $3 million per station. Most governments and industry consortium estimates suggest that the average cost would eventually drop to closer to $1 million per station and possibly even more than that in the future. Once completed, the hydrogen fueling station will look and operate like a traditional CNG fueling station, including the storage, compression, and production equipment. Depending on how permanent installations are, piping and electrical equipment may be above or below ground. The total footprint of a hydrogen fueling station is close to that of a diesel or CNG station that operators may already own and operate. Hydrogen fuel cell and battery electric buses both need constant electricity supply. When electricity supply is disrupted due to a power outage from natural disasters or planned grid maintenance, the service will be affected. Operators should have conversations with utility providers about scheduled maintenance to avoid overlapping with charging periods and assess what types of disruptions are likely to occur in the area, as well as service reliability reports and time it takes to restore electricity supply. Operators will also need to determine the minimal service needed to fulfill its missions should electricity outage becomes unavoidable. This helps identify whether additional infrastructure is needed to satisfy minimum service needs, either with power generators or battery packs. This is an open-ended question for different operator situations and is important to keep in mind. Here are some of the takeaway messages for this module. Supply of ultra-low sulfur diesel is needed for soot-free diesel buses. En-route and depot charging are two most common charging options for battery electric bus operators, and each has its own advantages. Depending on the type of power supply and charging speed needs, operators may adopt either AC or fast DC charging to fit their needs. A number of charging standards and protocols exist for battery electric buses and EVSEs. Utility companies and city governments are crucial partners for discussing electricity tariffs and land permits. Fuel cell electric buses utilize liquid hydrogen produced either on or off-site. The process operates like a CNG refueling station. Grid reliability and resilience to ensure continuity of service is important. These are the references and additional publications on the subject of soot-free and zero-emission technology infrastructure. If you have any questions, please reach out to me at y.xie@theicct.org. Thank you. Research and development of this curriculum is supported by Climate and Clean Air Coalition, the German Federal Ministry for the Environment, Nature Conservation, and Nuclear Safety International Climate Initiative, and Partnering for Green Growth and Global Goals 2030.